Imagine tonight being wonderfully still. Outside, the night sky stretches out like a dark velvet curtain, and on it, tiny stars shine with patient persistence. There's nothing to rush, nothing to prove. There is only you, your slowing breath, and that distant dome of sky that has been there long before humans ever appeared. Each fragile point of light is a distant sun, sending its glow across millions, even billions of years, just to arrive in this quiet moment. When you allow your mind to soften and let your imagination look upward, you quietly link yourself to a story that began long, long ago. Let a gentle thought drift in. The stars above you are not just decoration for the darkness. They're like clocks made of light, keeping the universe's history in their own way. The light you picture in your mind is actually a message that began its journey ages ago. Some stars are only a few dozen light years away, while others are so distant that their light left them before writing existed, before science existed, before anyone had a name for them at all. And when you think of that, the night sky suddenly becomes a vast archive of memories, where every star is an old record sealed by time. From within that stillness, a very gentle question arises. Could the first stars that ever lit up the universe still be out there somewhere? Long before the Milky Way settled into its shape, before the sun or earth were born, the universe passed through an age of almost complete darkness. And then, in that cold night, the first stars ignited, turning the quiet void into a place full of energy. Astronomers call them the first generation of stars, population 3, born from the nearly pristine material left over after the Big Bang. They were the very first torches, drawing the boundary between a cold, lightless cosmos and a universe full of galaxies, planets, gas, and dust. The question, are the first stars really still out there, may sound like a poetic headline, but in truth, it's a serious scientific problem. If we could understand the fate of those first stars, we would better understand why today's stars come in so many different kinds, why rocky planets exist, why there are oceans of liquid water, complex organic molecules, and eventually life capable of wondering and of looking up at the sky. In a deeper sense, by asking about the first stars, we are also asking about our own far-off origins, because the atoms in your body were forged in the cores of stars that died long ago. In this story, you don't need to chase every detail. Instead of forcing yourself to remember every name or number, just let your mind drift along with the narration. Think of each idea as a slow-moving image, like leaves gliding gently across the surface of a lake. You don't need to hold on to each one. Just notice that the water keeps flowing. The knowledge in this story won't arrive like a sudden downpour, but like a small stream, with ripples soft and steady. If there's something you miss or don't quite understand, that's perfectly fine. The universe took billions of years to write these stories. It's only natural for you to absorb them over a few quiet nights. Even so, each part of the journey carries its own meaning. When we talk about stars forming from cold clouds of gas, we're tracing back the moment of birth for stars in general, including the very first ones. When we mention a star's life cycle, from main sequence to red giant or supernova, we're learning how the universe recycles matter. When we look at ancient metal-poor stars or observe distant galaxies with modern telescopes, we're following the faint footprints of those first torches on the sky. Every small detail is a puzzle piece, and you only need to let them appear one by one until they quietly arrange themselves in your mind. More importantly, During all this, you're allowed to fully relax. There's no pressure to master the material, no exam, no scorecard. You only need to be here in this moment, letting the stories of the stars flow through you like a soft background melody. If your eyelids grow heavy, if your thoughts begin to blur like stars near the horizon, that's perfectly fine. The story is still here, and you can return to it anytime, just as the night sky always returns after every sunset. So let this opening chapter be a doorway into a strange yet gentle journey. Beyond that doorway lie nebulae nurturing newborn stars, other suns glowing around distant worlds, and faint signals from stellar remnants slowly cooling in the dark. And above all, the original question still hangs quietly in the air. Could the first stars still be out there, hidden in the dim light of the distant universe, in the chemical fingerprints of ancient stars, in every atom that now makes up your body? When you give yourself permission to slow down and lift your attention to the imagined sky, you might feel, in some delicate way, that those first stars are still whispering somewhere in the night. Everything else can wait until tomorrow. The sky and this story will stay with you. Under the imagined sky that unfolded in the previous chapter, where the stars felt like distant whispers of time, the story drifts slowly into a deeper layer of the universe's memory. And as the images settle softly, like a night breeze passing quietly by, a gentle question nudges us one step further. If tonight's sky is an archive of countless ages, then where is the very first chapter of that book? From that thought, our journey slides back toward a moment when even darkness had yet to meet the idea of light. It was a moment scientists call by a beautifully poetic name, the cosmic dawn. Not a dawn like the one we know, with the sun lifting itself over the horizon. This was a dawn with no sun at all, because before this instant, the universe did not possess a single star. It was simply a silent ocean of blackness, cold, vast, and seemingly endless, like a space where time itself hadn't yet decided what to place within it. Hundreds of millions of years passed in that darkness after the Big Bang, until the first clouds of gas began to gather, pulled together by a gentle but patient gravitational tug. Inside that darkness, something miraculous began to unfold. Primeval clouds of hydrogen and helium, the purest material remaining from the universe's birth, slowly condensed, swirling into dense pockets. They heated up, gradually building the conditions for a reaction that had never happened anywhere before. When the first nuclear fusion sparked, the first light burst forth, and with that light, the universe saw itself for the very first time. Those initial points of light were the population 3 stars, the primitive, primordial generation. They were nothing like any stars you've ever heard of or glimpsed through modern telescopes. They carried no iron, no oxygen, no carbon. Their bodies held only hydrogen, helium, and a trace of lithium, the simplest elements the universe created in the aftermath of the Big Bang. This purity made them burn differently, stronger, hotter, more violently than any stars that came afterward. Scientists believe these first stars may have been tens, even hundreds of times more massive than our Sun. Their surface temperatures soared so high that they could outshine almost any ordinary light. They radiated in brilliant blue-white, packed with ultraviolet energy powerful enough to transform the very matter around them. Each star was like an enormous torch illuminating a sky that had known nothing but darkness. Imagine them as the first sparks on a vast piece of cosmic wood, altering the night forever. But that fierce glow did not last long. The larger the star, the stronger the pressure inside its core, and the faster it burns its fuel. Population 3 stars lived fast, blazing as if they understood they were pioneers, meant to light the universe and then depart quickly. Their lifetimes were just a few million years, incredibly brief compared to the billions that fill the universe's history. They were born in darkness, flared brilliantly for a fleeting moment, and then vanished abruptly. It's likely that none of them survive today. Time swept them from the stage long, long ago. Yet their disappearance was not an ending. It was the beginning of everything that followed. In their violent deaths, many of them exploded as colossal supernovae, powerful enough to hurl billions upon billions of tons of gas into space. These explosions didn't just shine brighter than entire small galaxies. They became the universe's first forges of iron, carbon, oxygen, and countless other heavy elements, materials the early universe had never known. If the universe were a garden, the first stars would be the soil's very first enrichment. They left behind ashes rich in elements, the seeds needed for the next generations of stars, for rocky planets, for oceans, and eventually for living structures capable of observing the universe that shaped them. When you look at your own hand, the calcium in your bones, the iron in your blood, the carbon in your body, all of it was created in the cores of stars that died billions of years ago. And if you trace the lineage of those elements far enough, layer by layer, you finally arrive at the population 3 stars. They were the pathfinders, the torches that lit the first dawn, the universe's earliest jewelers. Even though they're gone, their legacy lingers everywhere. In the light of today's stars, in the chemical makeup of barren planets, in seawater, in mountains, and in every living thing. We can't see them directly, yet we live entirely within the world they created. With that understanding, the cosmic dawn no longer feels like an abstract idea. It becomes something like the universe's first deep inhale, a breath that set the entire cosmic symphony into motion. And that first light, though extinguished long ago, still echoes through every photon that reaches Earth today. If the previous chapter helped you hear the whispers of stars that still exist, then this one opens the door to the universe's first storytellers, the stars no human eye has ever seen, yet whose fingerprints are left on everything you know. From here, the story will drift forward into how later generations of stars were born, and how the universe gradually grew rich and varied as it is today. Let your mind rest and keep listening gently, because this journey is long and wonderfully soft. Ever since the first stars lit their glow in the universe's primordial darkness, a new chapter had begun. One where light and matter slowly took shape into the familiar structures we see today. And if the cosmic dawn marked the arrival of the very first torches, then the next chapter is the story of how countless generations of stars continued to be born, to grow, and to carry that narrative forward. From the primordial furnace of population through, the journey glides smoothly into a scene no less gentle. A place where new stars are conceived inside faint nebulae, where future light sleeps quietly within the soft shadows of gas and dust. Across the deep expanses of space, there are regions that look like dark, unremarkable clouds. But in truth, these are the most important places of all for star formation. They are cold nebulae, dreamlike nurseries where dust and gas drift in an almost motionless calm. Picture a vast sea of hydrogen gas, so immense that light would need years to cross it, with grains of dust floating like the ashes of stars long gone. Within these clouds, gravity, weak but persistent, keeps pulling pieces of gas together. When a region becomes dense enough, it begins to contract, as if the universe were gathering raw ingredients to prepare for the birth of a new beacon of light. One of the most beautiful and famous places humanity has ever observed is the Orion Nebula. To the naked eye, it appears as only a faint smudge of light, but through telescopes it reveals itself as a sprawling stellar nursery. Inside are thousands of protostars, each at a different stage of development. Every protostar is a collapsing pocket of gas, denser, hotter, spinning gently under gravity's guidance. If you could see it with your imagination, the interior of the nebula would appear like a quiet, tender realm where tiny dots of light are preparing to make their debut into the universe. As the gas cloud continues to shrink, its core heats up. A newborn star, known as a protostar, begins to form. It is not yet hot enough to shine brightly, but it already emits a faint glow in the infrared. That glow is like a fragile warmth slipping through the thick veil of gas and dust surrounding it. A small life still hidden but already fully present. At this stage, the protostar is still growing, pulling in more gas to increase its mass. It spins, contracts, shifts shape slowly, everything unfolding over hundreds of thousands, even millions of years. Inside the nebula, the universe never hurries. The floating spheres of gas in the darkness are not rushed constructions. They are embryos of light, nurtured by the universe's endless patience. Each gentle rotation, each gradual tightening of gas, each tiny rise in temperature is a quiet step toward a miraculous moment, when the star truly begins to burn. For a protostar to become a real star, the temperature and pressure in its core must climb high enough for nuclear fusion to ignite. When hydrogen is crushed to its extreme and begins merging into helium, an enormous burst of energy is released. It is the moment when the heart of the star begins to beat, a heartbeat made of light and power. Once fusion ignites, the star enters its true life. From there, it will shine steadily for millions or billions of years, depending on its mass. This is the moment the universe recognizes the arrival of a new member, a tiny sun within an endless sea of light. Yet not every protostar is fortunate enough to cross that threshold. Some gas clouds simply aren't heavy enough to ignite nuclear fusion. They can contract and warm a little, but they never reach the pressure required to burn hydrogen. These objects are known as brown dwarfs, failed stars, abandoned embryos of light. Brown dwarfs glow only faintly from leftover heat, mostly in infrared wavelengths, and gradually cool over time. If you imagine them in human terms, they resemble a small ember glowing softly in the night, slowly fading into darkness. Interestingly, despite being called brown dwarfs, their colors are not fixed. Depending on their temperature, they may appear slightly red, violet-orange, or just as a dim, ambiguous speck against the sky. Because they are so faint and so cool, they hide easily in the galaxy's shadows, so elusive that for centuries, humanity didn't even know they existed. Only with the development of modern infrared telescopes did brown dwarfs begin appearing in star maps, like quiet spirits of the cosmos coming into view. Whether they succeed or fail, every protostar is proof that the universe is always experimenting, always creating. In certain regions of the Orion Nebula, young stars collide with streams of gas, producing strange and beautiful ripples of light. In other regions, everything is calm, a single dim spark growing slowly in the dark. Each journey is its own version of the same ancient rules of gravity, temperature, and time. When we understand how stars are formed, we begin to see that the universe isn't only a place of violent explosions and colossal events. it is also a place of delicate, patient processes. Every star was once a tiny embryo inside a cold, dark nebula, each with its own timid beginning, preparing for its very first breath of light. If the previous chapter revealed the universe's pioneering torches, then this one uncovers the quiet truth that even now, the birth of stars continues silently throughout the galaxy. And as the story arrives here, the listener can imagine that within the vast darkness of the cosmos, new stars are always waiting to be born, softly, slowly, and with a patience that has guided the universe for billions of years. From the moment we witnessed the slow, patient formation of a star, from quiet clouds of gas to the instant nuclear fire ignited in its core, the story opens yet another door. And as that first light spreads outward, it marks not only the birth of a new celestial being, but the beginning of its place in a grand cosmic symphony, where every star carries its own shade of light like a unique note shimmering in the dark. When people look up at the night sky, the stars often seem like identical twinkling points. But upon closer attention, the sky reveals itself as a tapestry embroidered with many colors. Some stars glow pale blue like ice, others shine warm yellow like candlelight, and some burn with deep red-orange, like embers fading at the end of the day. Each star differs not just in brightness, but in color, and that color is a direct expression of its surface temperature. A blue star may be many times hotter than the sun, with a surface glowing at tens of thousands of degrees, producing shorter wavelengths of light. Meanwhile, red stars are cooler, their light softer, stretched toward longer wavelengths. From these differences, the night sky becomes a rainbow of temperatures, personalities, and stories. To understand this diversity more clearly, astronomers built a classification system based on stellar spectra, the ways stars emit light. This system, called Morgan-Keenan, uses 7 letters: O, B, A, F, G, K, M. It sounds simple, but behind it lies a long tale about how light reveals a star's inner nature. Stars of type O sit at the front of the sequence, blazing hot, blindingly bright, and extraordinarily rare. They are like the powerful opening notes of the universe's musical score. Types B and A are also bright and hot, though less extreme. Types F and G occupy the middle, their temperatures moderate. Our Sun is a warm, steady G-type star. At the end of the sequence are K and M stars, the coolest, smallest, and most common stars, glowing in gentle shades of red-orange. Because O, B, A, F, G, K, M can be difficult for beginners to remember, astronomers created a playful mnemonic. Oh, be a fine girl, kiss me. It has followed generations of astronomy students for decades, fun, simple, and memorable enough to hold on to a cornerstone of cosmic classification. But beneath the joke lies a profound truth. Through color and spectrum alone, we can determine a star's temperature, lifetime, size, brightness, and even its chemical makeup. Mass determines the fate of every star. The more massive a star is, the hotter its surface, the brighter its light, and the bluer its color. But this brightness comes at a cost. Massive stars live short, furious lives. An enormous O-type star may last only a few million years, a brief spark on the timeline of the cosmos. In contrast, the tiny stars at the end of the sequence, like type M, live so long that not a single one has died since the universe formed. They burn gently, softly, and steadily for tens of billions of years, far longer than the universe's current age. Every color becomes a story of time. Blue is the blaze of youth, intense, fierce, and short-lived. Yellow is the warm steadiness of maturity. Red is the long, enduring glow of patience and frugality. Once we understand this, the night sky stops being a collection of random dots and becomes a sweeping timeline, where each star lives out its own unique age and destiny. And what's fascinating is that stellar types aren't frozen categories. They connect naturally, because a star can shift from one type to another throughout its life. A star like the Sun begins as a G-type main sequence star, shining with a warm, steady yellow. But as the hydrogen in its core is depleted, it will swell into a red giant, shifting into the soft red-orange tones of a slow, deep musical note. When its outer layers drift away, the remaining core will become a white dwarf, a faint blue-white ember, small but incredibly hot. Over the course of its lifetime, a star can move through several colors, several phases, like a symphony passing from its introduction, through its crescendos, into its final quiet measures. Imagine each star as an instrument in the universe's orchestra. Type O and B stars are the trumpets, loud, powerful, echoing briefly. Types A and F are like violins, clear, balanced, graceful. Type G stars, like our Sun, are the cellos, warm, steady, anchoring the music. And types K and M are the soft wooden flutes, gentle, persistent notes stretching across time. Together, they form a performance that has been playing for billions of years, never stopping. And like any symphony, no section exists alone. When a G-type star ages, it shifts into the red tones of a giant. When it fades into a white dwarf, it takes on a pale blue-white glow, cooling slowly over eons. Massive blue stars, after burning through their fuel, may explode as supernovae and leave behind neutron stars or black holes. These remnants no longer shine like ordinary stars, but they are the drumbeats of the cosmic score, creating dramatic shifts in the fabric of matter and energy around them. So when you look up at the sky, the colors of the stars are more than beautiful visuals. They are timekeepers, slow, luminous notes playing from billions of years ago. Each star you see is a moment in its long, unfolding life. Some are young, bright, and blazing. Some are in their quiet final chapters. Some are in transition, shifting between colors and stages like variations in a melody. If the previous chapter brought you into the tender birth of young stars, this one expands the view so you can see the entire orchestra of light they join. And as the story continues to drift softly through your thoughts, you can imagine each star in the sky as a note sounding through time, connecting past, present, and future in a cosmic symphony written long before we ever existed. From the cosmic symphony of Starlight, where shades of blue, yellow, and red blend into a wondrous ribbon, the story opens again in a subtler direction. And as we listen more closely to the deepest, softest, most enduring notes in that vast harmony, we arrive at a group of small but steadfast stars, like whispers stretching quietly across billions of years in the darkness of space. Red dwarfs are those tiny, persistent beings. In the grand world of stars, they occupy the smallest corner of the main sequence, usually holding only about 0.1 to 0.5 times the mass of the Sun. When people imagine a star, they often picture a blazing, brilliant sphere of fire filling the sky. But red dwarfs choose a different path. They shine faintly, in gentle reddish-orange tones, so dim that without a telescope, almost no one would ever notice their presence in the Milky Way. Their light does not dazzle or demand attention. It seeps out softly, like embers glowing beneath a thin layer of ash, quiet, steady, and warm enough to show that something small and enduring is still alive. What makes red dwarfs remarkable is not their appearance, but their astonishingly slow pace of life. While massive stars consume fuel like roaring torches, burning fiercely and dying young, red dwarfs behave more like tiny oil lamps, burning each drop of fuel with meticulous patience. Their energy use is so efficient that their lifespans stretch beyond imagination. Some models predict that a red dwarf could live for trillions of years, nearly 100 times longer than the current age of the universe. That means not a single red dwarf has ever died since the universe began. Every red dwarf that exists today is still alive, still glowing with its soft red light in the cosmic night. If you imagine time as a river flowing endlessly, red dwarfs are like grains of sand resting quietly at the bottom, watching generations of other stars form and fade while they themselves remain untouched. They do not explode as supernovae, do not blaze like blue giants, do not expand into dramatic red giants. Instead, they burn slowly, silently, as if promising that even the smallest light can last forever when cared for gently enough. And amazingly, despite their modest size, red dwarfs make up the majority of stars in our galaxy. About 75% of the stars in the Milky Way are red dwarfs. That means most of the points of light you detect through a telescope are tiny red lanterns glowing somewhere in the dark. Yet ironically, almost none of them can be seen with the naked eye, their light simply too faint. Everything you see in the night sky is only a tiny fraction, a thin slice of a galaxy filled with quiet, persistent glimmers. A special example is Proxima Centauri, the closest star to the Sun. Even though it lies just 4 light-years away, it is far too dim to be seen without a telescope. There is something poetic about the fact that our nearest stellar neighbor is a quiet red dwarf, humble, understated, like a neighbor who lives right next door yet remains unnoticed. Proxima Centauri is a reminder that some of the most significant things in the universe are not always the easiest to see. Despite their long lives and stable nature, red dwarfs are not entirely calm. Many of them have magnetic fields far stronger than the Sun's, and they occasionally erupt with sudden flares. These bursts can cause their brightness to spike for minutes or hours before fading back to normal. This gives them a curious personality, gentle companions who, every so often, have a brief moment of flare-up, like someone who is kind and quiet, but capable of a sudden emotional spark. Even so, scientists still consider them far more stable and enduring than most other types of stars. These flares also matter for the search for life beyond Earth. Many planets around red dwarfs lie in the so-called habitable zone, where liquid water could exist. But strong flares may strip away the atmospheres of close orbiting planets, making survival difficult. In this sense, red dwarfs are both hopeful and challenging for anyone looking for life in the cosmos. Yet in the soft, bedtime nature of this story, we simply imagine them as small lanterns that occasionally flicker and then settle back into peace. Thinking of red dwarfs scattered throughout the universe brings a deep sense of quiet. They are not brilliant, but they feel like end-of-day warmth, like embers still glowing in the cold night. They don't compete with large stars, don't show off their brightness. They choose instead to endure for as long as the cosmos will allow. In a universe constantly shifting and transforming, that endurance feels strangely comforting. And if earlier chapters introduced the bright giants or the colorful harmonies of the sky, then this chapter is like a soft background melody, reminding us that not all beauty comes from power. Some beauty comes from persistence, patience, and stillness, qualities red dwarfs possess naturally. When you pay attention to them, you can sense a rhythm that is incredibly slow, incredibly steady, incredibly soothing, like a lullaby stretched across billions of years. In that quietness, red dwarfs continue to burn, little by little, as if proving that sometimes the smallest and humblest things are the most enduring in the entire universe. From the steady red embers burning quietly in the darkness of the galaxy, the story leads us into an even more tranquil realm, one where light never quite reaches the brilliance of a true star. And as we listen deeper, down to the very floor of the cosmic orchestra, we encounter strange beings that are half star, half planet, existing silently along the thin boundary between two worlds. Brown dwarfs are those stars that never grow up, celestial beings whose light never fully arrives, like stories left unfinished in the universe's long tale of creation. They carry a name that feels both tender and mysterious: failed stars. Not because they did anything wrong, but because they never gained enough mass to walk the full path that ordinary stars are destined to follow. A brown dwarf holds a mass between 13 and 80 times that of Jupiter, larger than any giant planet, yet still not enough for a true star to ignite the nuclear fire in its core. For a real star to shine, it needs immense pressure to fuse hydrogen into helium. But brown dwarfs stop just short of that threshold. They contract, warming briefly, then settle forever into a state just below the point where stellar fuel can burn. Without nuclear fusion, a brown dwarf cannot glow in visible light like other stars. All it can offer is a faint whisper of infrared warmth, something only modern telescopes can sense. If we place it in a familiar image, a brown dwarf is like a fading ember left behind after a fire has gone out, still warm, but without the bright flame it once aspired to. It rests quietly in the dark, not radiant, not self-luminous, simply existing in its own subdued way. That faintness makes brown dwarfs incredibly difficult to observe. For most of astronomy's history, humanity didn't even know they were there. Only when infrared technology advanced did the sky begin revealing small, warm specks against the black. One of the most important discoveries was Gliese 229b, a brown dwarf found in 1995, orbiting a larger star. Its presence offered the first clear evidence that brown dwarfs truly exist, opening a new chapter in our understanding of objects that live between the worlds of planets and stars. The life of a brown dwarf unfolds in silence over billions of years. With no fusion to replenish its energy, it cools slowly with time. Its age is not measured in brightness or heat or color, but in the gentle fading of warmth across the long night of the galaxy. Through billions of years, it becomes colder and dimmer, drifting steadily toward an ending without light. And yet, that very quietness is what makes it unique. It represents a suspended state between two cosmic identities, neither fully star nor fully planet. Their existence raises fascinating questions about how the universe constructs its worlds. Why are some clouds of gas large enough to form planets, yet not quite large enough to form stars? What causes a protostar to stall just before it has the chance to ignite? Those questions give brown dwarfs their special allure. They remind us that the universe creates not only complete stars, but also countless in-between forms, each of them a different version of balance, limitation, and physical thresholds. And though hard to see, brown dwarfs may not be rare at all. Some scientists believe the Milky Way may hold billions of them, drifting unseen in the dark. They don't call attention to themselves. They don't light up the space around them. But they remain, like dim memories woven into the background of the night sky. When you look up, there may be thousands in your field of view, yet your eyes will never catch them. Thinking about that feels like discovering a quiet secret the universe has been keeping. Amid the dazzling stars floats a hidden layer of shadowy objects, these brown ghosts, drifting in silence, telling their story not with light, but simply by existing. They may not be true stars, yet they play an important role in how the galaxy distributes its mass and energy. If red dwarfs are steady lanterns that glow through the ages, then brown dwarfs are the lingering warmth of dreams the universe never quite completed. They remind us that not every journey reaches its destination, but every journey still has value. Their presence enriches the sky, adding depth and mystery to spaces that might otherwise seem empty. And in a comforting way, their quietness fits perfectly with the rhythm of the cosmos. They take part in no violent explosions. They do not race against time, burning fuel in a frenzy. Instead, they accept their humble place, resting on the fragile border between two kinds of worlds, enduring like deep bass notes resonating at the bottom of the galaxy's great symphony. If the previous chapter told of long-lived red dwarfs that shine patiently through the ages, then this one brings us deeper into quietude, into a realm where light is only a faint breath. And as the story continues to flow gently, we realize that even the faintest things have a place in the universe, a peaceful, silent, poetic place in the endless dark, from those quiet brown ghosts drifting through the darkness. The universe brings us back to a more familiar kind of light, warmer, gentler, and directly tied to our own existence. And as the silence of brown dwarfs fades like a deep bass note in a long melody, the next part rises softly, like a morning tune, where other suns glow with the same golden warmth as the one Earth calls home. Among the countless kinds of stars in the sky, there is a group humanity feels an especially tender affection for, not because they are the brightest, nor the rarest, but because they resemble the very star that nourishes life on our planet. These are G-type main sequence stars, the other suns scattered across the Milky Way, burning quietly with a steady, gentle rhythm for billions of years. Our sun is just one among many, a single grain of light in the vast ocean of the galaxy. When we look at the sun each day, it is easy to imagine it as something exceptional. But in the grand scale of the universe, it is an average G-type star. Not too large, not too hot, not too bright. With a mass roughly equal to one solar mass and a surface temperature of around 5,500 degrees Celsius, it emits a warm, golden glow, the very light that allowed oceans, continents, and life to flourish. Other G-type stars shine with a similar soft yellow hue, like delicate lanterns hanging in the quiet darkness of space. The stability of this type of star is a gift. While massive blue stars live fast and die violently, G-type stars live slowly over billions of years. A star like the Sun enjoys a main sequence lifespan of about 10 billion years, a long era of steady, reliable brightness. Right now, the Sun is only about halfway through its life, 4.6 billion years old, and still has around 5 billion years ahead before it becomes a red giant. That means the warm light that Earth receives each day will continue for a very long time, far beyond any measure that humanity typically imagines. G-type stars are not only stable, but also excellent cradles for planetary systems. Many planets with mild climates are found orbiting such stars because their soft golden light and moderate energy output create wide, habitable zones where liquid water can exist. Earth itself is evidence that a planet orbiting a G-type star can develop a complex, rich, and lasting ecosystem. That is why, when humanity searches for life beyond Earth, G-type systems are often the ideal places to begin looking. What makes the story poetic is that our sun is not unique in this nature. Across the galaxy, millions of stars share its warm yellow glow. Some are very close to us. For example, Alpha Centauri A, part of the Alpha Centauri system, is also a G-type star, golden and warm like our sun. It is our nearest stellar neighbor, just a little more than 4 light-years away, residing in a triple star system where each member tells its own story of formation and evolution. Or consider Capella, the brightest star in the constellation Auriga. Capella is not just a single star, but a system of several stars, including luminous yellow giants. Its name comes from Latin, meaning little goat, born from ancient human imagination gazing at the sky. These names are not mere labels. They are memories woven from thousands of years of observation, when people looked at Starlight and filled it with stories, symbols, and gentle reflections of the natural world. Like our sun, other G-type stars follow their own evolutionary paths. They begin with long, stable lives on the main sequence, balanced between gravity pulling inward and thermal pressure pushing outward. Then, as hydrogen in their cores runs low, the core contracts and the outer layers expand, turning the star into a red giant. Ultimately, when the outer shell drifts away, the core shrinks into a white dwarf, a dense, hot remnant about the size of Earth, yet holding most of the star's original mass. This gentle ending reminds us that even the most stable stars have a soft twilight, not the violence of a supernova, but a slow shift from gold to red, then to a pale, fading white. And the charming part of their story is that G-type stars are not rare. They do not dominate the galaxy like red dwarfs do, but they are plentiful enough to form a significant stellar community. And because their light is soft, yet not too faint, we can see many of them with the naked eye on a clear night. Each yellow glow you notice may be another sun, with its own family of planets, and perhaps with worlds quietly watching their star the way we watch ours. If red dwarfs are steadfast companions, and brown dwarfs are unfinished dreams, then G-type stars are like reliable neighbors, steadily lighting their surroundings, creating the conditions for life to blossom. They are neither too grand nor too modest, sitting comfortably in the middle, balanced, harmonious, like a perfectly placed note in the cosmic symphony. In this gentle shift of tone, as the story flows toward these other suns, we begin to understand that the sun is not special because it stands alone, but because it belongs to a warm, steady, life-friendly community of golden stars. And among all that light, Earth found its place around one star whose conditions were so ideal that life could rise. When night falls and the sun's final golden rays yield to the dark, remember this: across the vast universe, countless other suns continue burning slowly, gentle, steady, and full of potential for life. From the warm golden suns burning steadily across the galaxy, the story expands into another dimension of the universe, one where the lives of stars are not always solitary journeys. And as the gentle glow of G-type stars spreads across the sky, we find something both natural and beautiful. Many stars do not live alone. They move through space with a companion, sharing an orbit, sharing a rhythm, drifting together through the quiet. In the vast universe, loneliness is not the norm. In fact, most stars are born in groups, emerging from the same cloud of gas, and many remain bound together for their entire lives. Binary star systems are the clearest example of this. Two stars orbiting one another like dancers performing a gravitational waltz. a waltz that can last millions, even billions of years, every turn soft, steady, unhurried, and unwavering. To observers on Earth, two stars eclipsing each other create moments of quiet wonder. When one star slips in front of the other, their combined light dims slightly. When the eclipse ends, the light brightens again. These rhythmic changes are known as variability, and they make certain stars appear to blink with a reliable pulse. The star Algol in the constellation Perseus is a famous case. In ancient times, people watched Algol shift from bright to dim and back again without knowing the cause. They named it Al-Ghul in Arabic, the demon star, because it seemed like a dark eye opening and closing with uncanny regularity. Only with modern astronomy did we learn that the effect was not an omen or a mystery of spirits, but the graceful orbit of two stars passing in front of each other. Among the countless binary systems, one of the most famous is Sirius, the brightest star in Earth's night sky. On clear nights, Sirius shines like a brilliant blue-white beacon, almost impossible to ignore. Yet that radiance does not come from a single star. Sirius is a binary. Sirius A, the bright star we see, and Sirius B, a tiny but incredibly dense white dwarf. In 1862, astronomers first detected Sirius B through a telescope and were astonished to learn that it was about the size of Earth, but held nearly the mass of the Sun. That discovery opened humanity's first real understanding of degenerate matter, an extraordinary state where material is compressed beyond what ordinary physics would predict. The partnership of Sirius A and Sirius B has become one of the night sky's quiet stories. A luminous giant and a small, faint companion circling each other in a slow, enduring dance. Their steady motion reminds us that even among familiar stars, hidden subtleties lie waiting for those who look with patience. Not all binary stars live peacefully. In some pairs, the closeness becomes a dangerous game. One star may siphon material from its partner, heating its own surface and sometimes flaring brightly. Astronomers call such systems vampire stars, because the larger star practically drinks the material of the weaker one. When the stolen material builds up enough, the surface of the vampire star can erupt in a sudden flash called a nova, a brief flare of light before settling back into quiet. This is not the catastrophic destruction of a supernova, but more like a powerful breath, a burst of emotion that lights the system before it returns to calm. Systems like these make the universe feel alive, full of stories. Some stars orbit each other with periods that span centuries. Others whirl so quickly that they complete a revolution in mere hours. Some systems contain 3 or 4 stars rotating around a shared center, like a complex musical ensemble with multiple players. Each one is a symbol of connection and motion, and these binary and multi-star systems are far from rare. Most stars in the galaxy are born within huge clouds of gas, where chaotic flows can split the collapsing cloud into 2 or more fragments, each forming a star. Bound by gravity, these stars remain companions for life. If you look at the night sky and imagine each bright point as a solitary star, the reality is far more intricate. Many of the stars, seen with the naked eye, are actually multiple stars whose combined light blends into one. Only powerful telescopes can separate their glow, like teasing apart the notes of a chord. In observing binary and multi-star systems, we see that the universe is not merely a place of isolated objects, but a realm of relationships that endure for billions of years. These relationships are not tight constraints, but spacious orbits, paths wide enough for each star to keep its freedom. yet close enough to stay gently connected to a companion, balanced between distance and attraction. If the previous section explored the warm suns capable of nurturing life, this one offers a different perspective. Those suns, and many others like them, often live in long-lasting, harmonious partnerships. And as the story continues to flow like soft starlight across the universe, we can imagine millions of pairs of stars dancing around each other, writing delicate motions that never stop. From the pairs of stars spinning around each other like passionate dancers in the endless dark, the story opens into a new chapter. One where that rhythm slows, warms, and softens into the colors of a cosmic sunset. And as the gentle motion of binary stars fades away, we meet another image of stellar maturity, the moment when stars drift into old age and quietly swell like soothing red embers glowing in the night. In the long journey of a star, its youth is spent in steady balance. Hydrogen fuses smoothly into helium, and light flows outward in a familiar rhythm. But like all living things, even the most powerful celestial bodies eventually reach a point when their primary source of energy begins to decline. As the star's core runs low on hydrogen, its internal structure falters. Gravity pulls the core inward, causing it to contract and heat up, while the outer layers expand, ballooning outward like a vast crimson cloak. This is when a star enters its red giant phase, one of the most beautiful, melancholy, and awe-inspiring sights in the sky. Red giants are not always radiant in terms of brightness. Their light softens, shifting into shades of orange or deep red, because their surface grows cooler than it once was on the main sequence. Yet their size grows in unimaginable ways. A star once similar in scale to our Sun suddenly expands tens of times over, becoming a colossal red sphere suspended in space, beating out the final slow pulses of a life that has lasted billions of years. A prime example is Arcturus, the red giant in the constellation Boötes. Arcturus is about 25 times larger than the Sun, and its warm orange glow was once used by ancient peoples to guide the seasons. Its name comes from the Greek word meaning guardian of the bear, because of its position near Ursa Major. The image suits it. Arcturus feels like a silent sentinel of the sky, an elderly flame that has witnessed many cosmic cycles, yet continues to burn with its own quiet grace. Observing Arcturus feels like watching a sunset unfold across its surface, deep, gentle, and dignified. If Arcturus is a tender ballad of cosmic old age, then red supergiants are full symphonies. These stars are massive, often at least 8 times heavier than the Sun. So when they reach their final stages, their expansion is far more dramatic. A red supergiant can grow as wide as Jupiter's orbit or even larger, swallowing any inner planets that may once have circled it. These stars are not merely red spheres. They are enormous celestial bonfires, brilliant but delicate, beautiful in a way that feels almost otherworldly, as if they belonged to a parallel universe with its own rules of scale. Betelgeuse, the bright star marking the left shoulder of Orion, is perhaps the most famous red supergiant. It is about 900 times the size of the Sun. To put that into familiar terms, if Betelgeuse were placed where our Sun is now, it would swallow Earth, engulf Mars, and stretch close to Jupiter's orbit. The world took notice when Betelgeuse dimmed dramatically in 2019, sparking speculation that it might soon explode as a supernova. But even if that were true, soon, for a supergiant, can still mean tens of thousands of years, longer than the span of every human civilization combined. Betelgeuse glows with a soft reddish-orange light, like a gigantic heart beating incredibly slowly, each pulse measured not in seconds, but in millennia. When red giants are mentioned, people often wonder what will happen when our sun reaches that stage. The vision is both frightening and strangely beautiful. If Earth still existed and could watch the sun turn into a giant, the sky would transform into a dome of red light, devouring what we once called daytime. The blue of the sky would vanish, replaced by a permanent dusk. The horizon would look as though it were smoldering gently, and the oceans would boil long before disappearing entirely. But all of that lies 5 billion years in the future, so far away that every living person today can drift into sleep without the slightest worry. All that matters now is the beauty of the red giants we observe from afar, like elderly suns casting their soft orange glow through the darkness, hanging in space like sunsets and sunrises frozen in midair. In the silence of space, these aging stars remind us that a star's story is not only in its youthful brilliance, but also in its meaningful later years, when it returns material to the universe through layers of gas drifting outward, enriching space for future generations of stars. From that, the cycle continues. Atoms released by red giants may one day become the seeds of nebulae, then condense into new stars, new planets, and perhaps even new life. So when we look at a red giant, we are not only witnessing an ending, we are watching the preparation for a beginning. A cosmic sunset always travels hand in hand with a dawn somewhere far away. And in that gentle transition, we understand that the universe has never been still. It has simply been breathing in its own quiet rhythm. From the deep crimson sunsets blooming across the cosmos, the story of stellar life drifts onward like a long, quiet breath of the universe. And as those red hues fade gently into the dark, another world of light begins to appear. A world where stars do more than shine. They flicker, they tremble, and they change with mysterious rhythms, as if each one possessed a heartbeat of its own. In the stillness of the night sky, some stars are never constant in brightness. They glow brightly at times, then dim, then brighten again, following cycles that may be regular or unpredictable. These shifts are not tricks of the eye, but true behaviors of the stars, born from their inner structure and motion. These are variable stars, the heartbeats of the sky, where each pulse of brightness and shadow feels like the universe itself is breathing, living, and moving to a rhythm only patience can reveal. The idea that the universe contains stars with their own changing pulses holds a deeply human beauty. Just as a heart expands and contracts to maintain life, some stars swell and shrink in a steady cycle, causing their light to wax and wane with each beat. Among them, the most iconic are the Cepheid variables. These stars are far larger than the Sun, yet what makes them remarkable is their constant expansion and contraction. Each cycle lasts from a few days to several dozen, and when the star swells, it brightens. When it contracts, it dims. One special Cepheid is Delta Cephei, the star from which the entire class takes its name. In the 18th century, a young astronomer named John Goodricke was the first to record its regular pattern of brightening and dimming. At the time, astronomy lacked the tools to explain such behavior, yet the pattern was so clear that it could not be ignored. Many years later, in the early 20th century, Henrietta Leavitt, a quiet, meticulous woman working at the Harvard Observatory, discovered something extraordinary. The longer the Cepheid cycle, the brighter the star. Her discovery entered the history of astronomy as a testament to patience and precision. Thanks to Leavitt, humanity gained its first standard candle for measuring cosmic distances. Over time, that story became one of the most poetic chapters in science. A woman sitting silently before thousands of photographic plates, counting tiny shifts in starlight, ended up unlocking the scale of the universe. In the language of tonight's telling, she becomes almost a fairy tale figure, the girl who decoded the sky, turning pulses of light into numbers that reshaped our understanding of space. But Cepheids are not the only variable stars that captivate us. Long before science understood their nature, Mira, a star in the constellation Cetus, astonished humanity. Mira can be bright enough to see with the naked eye, only to vanish for months, then reappear as if reborn. Today we know Mira has a cycle of about 330 days, but in 1596, when astronomer David Fabricius observed it, this was nothing short of a heavenly omen. He named it Mira, meaning wonderful, and that name remains fitting even now. Under ancient night skies, people likely watched Mira disappear and return, imagining it as a message from the heavens. In an age before artificial light drowned the stars, every change in brightness carried weight. Mira's peculiar dance became woven into human imagination, a gem that appeared and vanished with the universe's breath. There are also variable stars caused by eclipses, especially the famous Algol, the demon star mentioned earlier. Because Algol belongs to a binary system, when one star passes in front of the other, its light to Earth dims and then brightens again, with remarkable precision. Ancient people could not know this. They saw Algol's steady blinking like an eye opening and closing in the dark and believed it was ominous. Science has long explained the phenomenon, yet the mystery it evokes still lingers whenever we look at it. Variable stars do not change only because of pulsations or eclipses. Some flare violently when material falls onto their surfaces, creating novas. Others flicker due to intense magnetic fields. Some rotate so quickly that their brightness fluctuates with each spin. The universe seems to have no limit to the ways a star can alter its light. And in each of these variations, we sense something uncannily human. The brightening and dimming of variable stars resemble the beating of enormous hearts far away. Each star has its own pulse, its own rhythm, its own story. Some cycles last days, others last a year, others may span longer than a human lifetime. Yet no matter the rhythm, they compose a symphony of light, each star whispering to Earth, "I am here. I am still breathing." So when you look up at the night sky and see a star suddenly shine brighter or fade, it might be a Cepheid swelling with light, a Mira returning from a long cycle, or a binary star gently eclipsing itself. But whoever it is, that change is part of the universe's heartbeat. And in that rhythm, you may feel a quiet connection between yourself and the sky. That the human heart and the hearts of stars, though separated by unimaginable distances, are beating together in the same long music of time. From the steady pulses of starlight, like the quiet heartbeat of the sky, the story of variable stars brings us closer to the subtle movements of the cosmos. And as that light settles, as though the universe has just taken one deeper breath, we enter an entirely different realm, one where light is no longer gentle or slow, but erupts with the raw force of primordial fire. Among the countless trillions of stars scattered across the galaxies, only a precious few possess nearly unrivaled power. These are the scorching blue giants, immense cosmic titans that shine with blinding blue-white intensity, like radiant torches burning fiercely against the darkness. They belong to the O and B spectral classes, rare, strong, extraordinary, so luminous that no galaxy can hide their presence. The surface temperature of an O-type star can exceed 30,000 degrees Celsius, and their brightness can reach hundreds of thousands of times that of the Sun. In the skies of a distant galaxy, a single O-type star can illuminate an entire nebula. One of the most famous examples is R136A1, buried deep within the Tarantula Nebula of the Large Magellanic Cloud. With an estimated mass of 250 suns, it is considered one of the heaviest and most luminous stars ever discovered. Its sheer scale defies ordinary imagination. If the Sun is a gentle flame, then R136A1 is a colossal pillar of fire roaring in the darkness, a force so intense that no earthly image can fully capture its magnitude. But like all celestial things, the brighter something burns, the faster it fades. O-type stars live extraordinarily short lives, only a few million years. Compared to the universe's 13 billion year age, their existence is like a single flash of lightning. They live fast, die young, but leave profound imprints on the cosmos around them. Ionizing gas, lighting up nebulae, sculpting interstellar clouds, and laying the groundwork for the stars that follow. In the evolutionary journey of these colossal stars, there is a phase so rare and so strange that simply speaking its name evokes reverence in astronomy. This is the Wolf-Rayet phase, WR stars for short. These are massive stars shedding their outer layers through powerful stellar winds. These winds blast material outward at thousands of kilometers per second, gradually revealing the scorching core beneath. The surface temperature of a WR star can reach up to 200,000 K, so hot that no known material on Earth could endure it. Their spectra feature strong emission lines, signs that they are expelling gas in fierce interstellar storms. This gives WR stars the appearance of giant warriors casting off their armor, exposing raw blue-white fire just before collapsing in a supernova. Wolf-Rayet stars are incredibly rare. In the entire Milky Way, only a few hundred have been identified. They are the rare blossoms of the stellar garden, brilliant, fierce, and fleeting. Their brief existence resembles a grand firework display in the night sky, dazzling, yet momentary. For this reason, it is uncommon to observe a WR star with the naked eye, and even rarer to witness one at its most beautiful stage. Astronomical history records that in 1867, two French astronomers, Charles Wolf and Wolf-Rayet, discovered the unusual spectra of three stars unlike any known before. Their intense, enigmatic emission lines inspired the classification Wolf-Rayet, a name that has since become iconic in the study of massive stars. One striking example of the WR class is Gamma Velorum, often called the spectral gem of the southern sky. Although more than 1,000 light-years away, it is still bright enough to be seen without a telescope from the southern hemisphere. Gamma Velorum is a multi-star system, with one component being a WR star whose spectral signature is considered a scientific masterpiece. But the beauty of WR stars extends beyond the stars themselves. Their extreme stellar winds often create shell-like nebulae, rings or expanding arcs of glowing gas surrounding the star like luminous petals. One of the most breathtaking images captured by the James Webb Space Telescope shows the nebula around WR124, resembling a flower of light blooming in the depths of space. It is a glimpse of a star in its final shedding, a series of radiant layers drifting outward as the star prepares for its ultimate act. A supernova explosion. When we gaze at blazing blue giants and Wolf-Rayet stars, it feels like watching the most dramatic chapters in the lives of stars. If red dwarfs live for trillions of years with steady endurance, O-type and WR stars exist for only the blink of an eye. Yet in that fleeting moment, they illuminate galaxies, shape their cosmic surroundings, forge heavy elements, and clear the stage for new generations of stars to be born. So although they are often called monsters for their fierce power and enormous size, in truth, they resemble explosive artists on the cosmic stage, burning with everything they have, shining impossibly bright, and leaving behind beauty that the universe carries for billions of years. And as the blue-white flames of these giant torches fade into the endless dark, the story continues, soft and quiet again. Like beams of starlight drifting through a nebula, from the brilliant blue torches that burn themselves out like cosmic fireworks, the story naturally drifts into a quieter region of space, one where light no longer dazzles, but softens into layers of ethereal mist. And as the fury of massive stars fades away, we encounter an entirely different scene. The fragile, deeply poetic beauty left behind by small and medium stars after their long journeys of billions of years. When a star like the Sun reaches the end of its healthy life, when the core can no longer sustain stable hydrogen fusion, its aging chapter begins. The core contracts, the outer layers expand, and the star enters the red giant stage, slow, steady, inevitable. And then, when the outer layers can no longer hold on, they are released into space in pulses, in shells, like the final soft breaths of a celestial body that has spent all its strength. These layers drift outward, spreading and thinning, eventually forming what we call a planetary nebula, a glowing shell of colored gas surrounding the exposed core. The name Planetary Nebula was an early misunderstanding. Through small telescopes, these round, smooth glows resembled planets. But within these halos lies no forming world, only the traces of a star closing the last page of its life. Planetary nebulae are among the most beautiful sights in the sky. Their light is not explosive like supernovae, not scorching like O-stars or Wolf-Rayet giants, but gentle, rounded, and soft, like watercolor paintings floating against the black canvas of space. A famous example is the ring nebula, M57, in the constellation Lyra. From Earth, it looks like a perfect glowing ring of bluish light, formed as layers of gas drift outward in a circular halo, like the lingering crown of a star whose inner brilliance has slipped away. Or consider the Owl Nebula, M97, with two dark, round patches inside the glowing shell, evoking the calm gaze of an owl peering through the night. The shape is not intentional. It simply emerges from gas flowing outward along two different axes. Yet the effect feels unexpectedly human, expressive, alive. One of the most intricate nebulae is the Cat's Eye Nebula, NGC 6543, where layers of gas are stacked in spirals, shells, and swirling folds, like luminous eyelids carved into space. Its delicate structure seems as if someone etched a multi-layered cosmic eye into the void. Watchful, silent, and profoundly deep. At the center of each planetary nebula lies the remnant core of the star, a white dwarf. White dwarfs are among the strangest objects ever discovered. Though only about the size of Earth, they pack nearly the mass of the Sun. This means their matter is compressed to astonishing density. A teaspoon of white dwarf material could weigh several tons, heavier than a large truck. This is the state of degenerate matter, where electrons are pressed so tightly together that they create an unusual kind of pressure, preventing further collapse. And though it appears as a small white point amid the nebula's glow, a white dwarf is still immensely hot, tens of thousands of degrees, cooling very slowly over billions of years until it becomes a dim, cold ember in the cosmic dark. A familiar example of a white dwarf is Sirius B, the tiny yet unbelievably dense companion of Sirius A, the brightest star in the night sky. When Sirius B was discovered, its extreme mass and tiny size shocked astronomers and changed our understanding of stellar physics. Sirius B proved that the death of a small star is far from ordinary. It leads directly into new chapters of physics and into strange forms of matter unknown on Earth. But perhaps the most enchanting white dwarf story belongs to BPM 37093, a star in the constellation Centaurus. In 2004, astronomers discovered that its core had crystallized into solid carbon, in essence, a giant diamond. This cosmic jewel weighs roughly 10 billion trillion carats. Scientists fondly nicknamed it Lucy, inspired by Lucy in the sky with diamonds. And the name, though playful, conjures a beautiful idea. When a star dies, it may leave behind a radiant crystal heart drifting softly through the night. Planetary nebulae and white dwarfs form the gentle closing chapter of small stars. Not fierce, not violent, but filled with tranquil beauty. They remind us that the universe is not built solely from explosions and blazing giants, but also from quiet, dissolving moments, final breaths that become art. When we look at a planetary nebula, we do not see only the death of a star. We see a graceful farewell, a colored cloud hanging in space, a tiny white core resisting time, a transformation from a lifetime of starlight into a new cloud of possibility. We see creation braided into destruction, softness born from collapse, and in those drifting layers of soft light, we are reminded that even endings can be gifts, something the universe can gather, reshape, and turn into new beginnings. From the silky, gauzy nebulae quietly drifting open around a shimmering stellar core, the story of the gentle death of small stars gradually gives way to an entirely different chapter of the universe. And as the last wisps of gas fade like thin smoke, we begin to hear the distant hum of a far more violent, far more intense kind of ending. One in which the sky does not merely witness a death, but a blast powerful enough to shake an entire galaxy. Some stars do not choose to leave in peace. They do not shed their outer layers bit by bit, the way the sun will someday do. Instead, massive stars, those 8 times the mass of the sun or more, end their lives in a blinding burst known as a supernova. It is one of the most powerful events the cosmos has ever created, bright enough to rival an entire galaxy for a few short weeks. To understand why this happens, let us step into the core of a giant star in its final seconds. After the star has burned through the light elements, hydrogen, helium, carbon, neon, oxygen, silicon, it gradually builds up an iron core. Iron is special. It cannot produce energy through fusion, and so when the iron core grows too heavy, the star can no longer resist the relentless pull of its own gravity. In a moment lasting only a fraction of a second, the iron core collapses, then rebounds, creating a catastrophic shock that blasts the star's outer layers into space at unimaginable speed. That is the supernova explosion. If a supernova occurred near Earth, perhaps Betelgeuse in the constellation Orion, the night sky would glow like a soft sunset. For weeks, you could simply step outside and see a brilliant new star with no telescope at all. Even from hundreds of light years away, its light would be bright enough to paint the night like the flame of a galaxy. Humanity has seen such a sight before. In the year 1054, ancient Chinese astronomers recorded the arrival of a guest star so bright it was visible during the day for weeks. A strange light, belonging to no known constellation, appeared without warning and then vanished. Like a mysterious omen no one could explain. Over 900 years later, modern astronomers discovered that the remnant of that event was the Crab Nebula. At its center, they found a neutron star, spinning rapidly and sending out steady pulses of radio waves, a leftover core that had collapsed and become the dense object we will explore later. Through old records and modern images, we now have a portrait stretched across time of a cosmic event that once reached all the way to Earth. What makes a supernova extraordinary is not just its blazing brilliance, but the creativity it sparks. In those impossible pressures and temperatures, violent nuclear reactions forge heavy elements the universe could not otherwise create: gold, silver, uranium, iodine. All of these were born in the fury of a supernova, then flung into space, mixing with clouds of gas to become the raw material for new stars, new planets, and even life itself. Which means the gold in your wedding ring was forged in a supernova. The calcium in your bones was once the ashes of a dying star. In a profound sense, we carry within us the legacy of cosmic explosions that occurred billions of years ago. A supernova is not only an ending, it is the rebirth of matter, the universe's way of shaping complexity from chaos. Humanity once witnessed another, closer supernova, Kepler's supernova of 1604. A new star appeared above Europe, stunning the scholars of the time. Johannes Kepler, one of history's great astronomers, spent months observing its changing light, recording every detail. This event helped shift humanity's understanding of the heavens, that the sky is not unchanging, that those distant points of light can die, and when they do, they create fireworks no civilization could ever imitate. Despite their violent nature, in tonight's gentle narration, we can see supernovae as the universe's radiant blossoms, a cosmic flower that blooms only once in millions of years, yet whose light travels trillions upon trillions of miles, leaving beauty etched into every wisp of its nebula. And when that hot gas slowly fades, drifting through the cold dark, we understand that the universe crafts beauty through both quiet and chaos. Planetary nebulae are gentle deaths. Supernovae are explosive ones, but both are essential chapters in the long story of the stars. In the dim glow of these remnants, the universe softly reminds us, from death, life begins again. And in every breath of the night sky, the light of ancient supernova is still traveling outward, carrying the stories of stars that once burned with everything they had, from the radiant supernova explosions blossoming like cosmic fireworks in the dark expanse. We know that such an ending is not a final full stop. When the outer layers of a star dissolve into space, leaving behind faint, drifting nebulae, the collapsed core continues on its own strange journey. And as the blinding light of the supernova fades, something unusual begins to reveal itself within the remnants. A heart so dense, it surpasses anything human intuition can truly grasp. When a massive star, many times heavier than the sun, reaches the end of its life and erupts as a supernova, what remains is not total dissolution. The star's core, instead of dispersing, is crushed under overwhelming gravity. The pressure becomes so immense that every proton and electron is forced together, merging into neutrons. The result of this extreme compression is a neutron star, one of the strangest objects in the universe. A neutron star is unbelievably small, only about 20 kilometers across, roughly the length of a small city on Earth. But its mass is nearly equal to that of the Sun. This means its matter is crushed to nearly absolute density. If you could scoop up a teaspoon of neutron star material, something no one could ever actually do, that teaspoon would weigh as much as Mount Everest. How could the universe create something so tiny, yet so unimaginably heavy? A neutron star is like an enormous atomic nucleus, where trillions upon trillions of neutrons are packed so tightly together that there is almost no empty space. Air, water, metal, rock, everything familiar to us ceases to exist here. A neutron star is an alien world, where matter takes on a completely different form, ruled by the most powerful forces in nature. Within that absolute compactness, some neutron stars possess another feature that turns them into beacons of the sky. When a neutron star spins rapidly, tens or even hundreds of times per second, and when its spin axis is tilted relative to its magnetic axis, beams of radio waves or X-rays sweep outward like symmetrical searchlights. As the star rotates and those beams sweep across Earth, we detect steady pulses. This phenomenon is called a pulsar. The first pulsar was discovered in 1967 by Jocelyn Bell Burnell when she was still a graduate student. She recorded eerily regular radio signals, each pulse separated by exactly 1.33 seconds. Their perfect rhythm led her research group to jokingly suggest the source might be alien life. They labeled it LGM-1, short for Little Green Men 1. But soon they realized these signals came from a rapidly spinning neutron star. And with that, the first pulsar entered the history of science. Since then, humans have discovered hundreds of pulsars scattered throughout the Milky Way and nearby galaxies. Each pulsar is like a cosmic clock, ticking with unwavering precision for millions of years. Each pulse is the distant echo of a star that has died, a gentle reminder that even when a star loses its brilliant outer glow, its core continues sending its final messages, like the immortal heartbeat of the universe. But neutron stars do not stop there. Among them is an even rarer and more astonishing kind, the magnetar. If pulsars already possess fierce magnetic fields, magnetars are truly the magnetic monsters of the cosmos. A magnetar's magnetic field can be 1,000 times stronger than that of a typical pulsar, and 1,000,000 trillion times stronger than Earth's magnetic field. This power is so immense that it can erase data from a credit card, distort electrons within atoms, unleash bursts of X-rays and gamma rays that ripple through space. If a magnetar were to appear near Earth, even from tens of thousands of kilometers away, its magnetic field could disrupt electronic devices. Fortunately, all known magnetars lie far from us, tens of thousands of light years away, where their light arrives merely as a distant whisper. Despite their strength, their violence, and their occasional danger, neutron stars and pulsars hold a beauty of their own. It is not the shimmering beauty of nebulae or the dazzling flare of supernovae, but a beauty rooted in endurance. A pulsar can spin for millions of years, sending out steady pulses like a heart that never stops beating. A star may have died, but its neutron heart continues, slow, rhythmic, sending a gentle message into the dark sea of space. You might imagine that somewhere, thousands of light years away, a neutron star is spinning in the night. Each rotation is a breath, a flicker of radio light sweeping through the cosmos, a whisper from a heart that has stopped burning, yet has never stopped living. And when we listen to those pulses through our telescopes, it is as if we are hearing echoes from the star's long-ago days, fragments of an existence that has ended, yet still wishes to leave its mark on the cosmic night. In the vast stillness, pulsars, magnetars, and neutron stars remind us that the death of a star is never the end. It simply opens a new chapter, denser, stranger, and deeper, a chapter we can only understand by listening with patience. From the steady heartbeat of a pulsar echoing like the last pulse of a star long gone, we understand that the end of a massive star is never as simple as disappearance. And as we step deeper into the final chapters of the largest lives in the universe, we encounter a remnant even more mysterious, more silent, and more solemn than anything light could ever touch. When a star with enough mass reaches its ultimate limit, gravity at its core grows so intense that no known force can resist it. Even the repulsive force between neutrons, strong enough to keep a neutron star intact and prevent further collapse, finally gives way. The core falls inward, shrinking into a point infinitely small and infinitely dense. That point is known as a singularity. Surrounding it is the event horizon, a silent boundary from which nothing returns. Not matter, not signals, not even light itself. And thus, a black hole is born, a realm of absolute darkness, the final transformation of a once brilliant giant. No more fusion burning hydrogen into heat, no more neutron heartbeats, just a region of space where gravity becomes so powerful it bends time itself. We call it a black hole, though that name captures only a small fraction of what it truly is. In reality, it is like a dent in the fabric of the universe, a place where every path leads inward and none lead out. There are many types of black holes, but here we focus on stellar mass black holes, those forged from the death of supermassive stars, weighing tens of suns. They drift through the galaxy, hiding at the deepest shadows, like ghosts invisible to the human eye. In contrast, there are also supermassive black holes, giants millions to billions of times the sun's mass, anchoring the centers of galaxies, including our own Milky Way. But that belongs to a scale far beyond the one we are exploring tonight. Stellar black holes remain our main focus, for they are closer, more common, and the most direct outcome of a massive star's life cycle. What makes black holes so uniquely mysterious is that we cannot see them directly. They emit no light, no clear signals. Yet we know they exist through the disturbances they create in the world around them. A famous example is Cygnus X1, a binary system where a normal star orbits an invisible gravitating companion. The visible star continuously loses gas to the unseen object. The stolen gas heats up, spirals into a glowing disk, and emits powerful X-rays that astronomers on Earth easily detect. When studied more closely, it became clear that the dark companion could not be a neutron star or any known stellar object. It had to be a black hole. Stephen Hawking once confidently bet that Cygnus X1 was not a black hole, perhaps because at the time, accepting such an object as real felt too bold. But as evidence grew undeniable, Hawking admitted defeat. The story is charming, but it also reveals how even the greatest minds once hesitated before the strangeness of black holes. Despite their ominous name, black holes do not roam the universe devouring everything in sight like movie monsters. If the sun were replaced by a black hole of equal mass, Earth's orbit would remain unchanged. Our planet would continue circling steadily. It would simply be plunged into permanent darkness. Black holes do not suck things in indiscriminately. They only consume what ventures too close. Most of the time, a black hole simply rests, hibernating unnoticed. It becomes violent only when a star, a cloud of gas, or some drifting object crosses into its danger zone. Then the gas heats up, spirals into a brilliant disk, and releases intense energy, sometimes creating a quasar, one of the brightest beacons in the universe. But this brilliance is often fleeting. Afterward, the black hole returns to its quiet darkness. The very idea of black holes can make some people uneasy, yet within the context of a sleepy, soothing narrative, there is another way to see them, as places of absolute stillness. While variable stars flicker, blue giants blaze, and neutron stars pulse, a black hole remains perfectly calm. No light, no visible motion, no external turbulence. It is a region where time nearly stops, where silence reaches its purest form. If we imagine the universe as a grand symphony, a black hole is one of its deepest rests, a pause where every sound dissolves into stillness. It exists not as a threat, but as a reminder that even in the vastness of space, there are pockets of quiet, empty spaces, places where movement gives way to silence. And within that quiet, black holes become gentler than we imagine. Not predators, but soft punctuation marks ending the luminous lives of colossal stars. They mark the final dot of a brilliant journey and open a silent realm where light cannot enter. Yet human imagination can wander farther than ever. If we listen long enough, sometimes silence becomes the most soothing sound in the universe, from the quiet shadow of black holes, those places where light can no longer return. The story of stars seems to reach its farthest edge. But our journey does not end there. Because long before massive stars collapsed into black holes, long before neutrons and pulsars came to be, the universe once held other stars, older, lonelier, and more ancient than anything we know today. They linger like faint echoes from the dawn of time. And now, we trace their remnants, like discovering glittering fossils scattered across the vastness of space. Throughout our exploration of stellar life cycles, we have traveled from bright young stars to aging giants, watching them explode or fade into strange remnants. But one question has always remained. Is there a star old enough for us to hear the breath of the universe at its very beginning? That question led astronomers on a search for the elders of the Milky Way, stars that have lived for tens of billions of years, seemingly among the oldest surviving witnesses of cosmic history. In the Milky Way, a handful of stars have ages that make scientists pause. They are not dazzling or fierce, nor are they compressed remnants of violent endings. Instead, they are faint, simple, and quietly present. Yet their very quietness makes them precious. They were born long ago, close to the moment when the universe first formed. They are living fossils, stars that carry within them the chemical traces of the ancient cosmos. One of the most famous examples is HD 1483, often called by its poetic, symbolic name, the Methuselah star. The name comes from the longest-lived figure in the Bible, because this star's age seems to stretch the limits of what we can imagine. Methuselah lies about 190 light-years from Earth, not far at all by cosmic standards. But its proximity isn't what astonished astronomers. It was its estimated age, roughly 14.5 billion years. That number is nearly equal to, and at times seem to exceed, the measured age of the universe itself, which is 13.8 billion years. Of course, no star can be older than the universe. For a time, this too-old star puzzled scientists. But after refining models and accounting for measurement uncertainties, they realized Methuselah had not broken any rules. It is old, but not older than everything. Its true age fits perfectly with the idea that it is a second-generation star, formed soon after the first stars, population 3, exploded and released small traces of metals into space. Astronomers confirmed this by studying Methuselah's chemical makeup. Its light reveals that it contains almost nothing but hydrogen and helium, with an extremely tiny amount of heavier elements. This tells us it formed in a universe that had barely been enriched by earlier generations of stars. If the universe were a field, Methuselah would be one of the first leaves to sprout after the very first rain. But Methuselah is not the only ancient star that captured scientific attention. 2025, a new discovery stunned the astronomy community. A red giant on the outskirts of the Milky Way was found with a chemical signature almost unheard of. It was nearly pure, containing an extraordinarily low amount of metals, setting a new record. A red giant, after billions of years of existence, should have accumulated some metals in its composition. But this star was so metal-poor that astronomers called it a pristine star, a star born from almost untouched material. Such purity is only possible if it was formed from matter released by the very first stars, those that exploded 13 billion years ago and seeded the universe with only the faintest trace of heavier elements. The existence of this pristine star is like hearing the softest, most distant echo from the dawn of the cosmos. If the first stars were the flames that lit up the darkness after the Big Bang, then this pristine star is the lingering ember, carrying the chemical imprint of that very dawn. The term stellar fossil is no longer just a metaphor. These stars are fossils in the truest sense. They have barely changed over billions of years, and their chemical compositions preserve the conditions of the early universe, like pages of a book whose ink has never faded. They dwell in peaceful regions of the galaxy, its faint outer halo, where star density is low and disturbances are rare. There, they are not torn apart, not swallowed by black holes, not scorched by active star-forming regions. They simply hang in the dark, living slowly and quietly, like old storytellers sitting in a quiet corner, waiting for someone to listen. When astronomers look at the faint glow of a star like Methuselah, they are not merely observing a point of light. They are reading an ancient message written in the language of chemistry, carrying memories of the first explosions, the first elements, the first light that ever threaded through cosmic darkness. In a way, these stellar fossils are keepers of memory. They preserve the opening chapters of the universe, chapters no living thing can recount except for them. And when we look up at the sky and see a faint, steady, unhurried light, we may well be gazing upon one of the oldest witnesses in existence, a star that has seen everything since time itself was young. Amid the deep darkness surrounding the Milky Way, these ancient stars continue to whisper their stories, slowly but clearly, their light crossing tens of billions of years just to reach us in this exact moment. From the fossil stars quietly resting on the galaxy's outskirts, we know the universe still keeps some of its oldest memories tucked away. And as we gaze at their faint, gentle light, a familiar question drifts back to us, distant yet intimate. If these second-generation ancient stars are still here, then is there any chance the very first stars, the Pop 3 generation, might still exist somewhere in the darkness? Across the entire history of cosmic exploration, very few questions are both as challenging and as poetic as this one. The first stars, formed just a few 100 million years after the Big Bang, were the very first flames to pierce the primordial darkness. They were the pioneers, the universe's earliest chemical architects, forging the heavy elements that made later stars, planets, and eventually life possible. But according to every physical model, those stars were too massive, too hot, and far too short-lived. Only a few million years after their birth, they likely all exploded, leaving behind nothing but ash and echoes. So the question, do the first stars still exist, is not really, are they still alive? But rather, can we find any trace of them at all? That is the journey of this chapter. The search for the fingerprints of Pop III, the search for the very first light of the cosmos. Astronomers approach this search through two different pathways, like twin streams flowing toward the same ocean of understanding. The first path is the hunt for extremely metal-poor stars within our own Milky Way. In the previous section, we met Methuselah and other stars with nearly primordial chemical compositions. They are not POP3, but they may be the direct descendants of their ashes. So if we can find a star with almost zero metals, almost perfectly pristine, we might be standing very close to the shadow of the first stars. The second path is to look outward into deep space, where light takes billions of years to reach Earth. When we observe far enough, we are effectively looking into the past, seeing the universe as it was when it was still young. Observing far into space is like replaying the first frames of the universe's film, and within those frames, we may catch the glow of pop-through stars. That is why, in 2025, when the James Webb Space Telescope was reported to have found hints of pop-3 stars in a galaxy 13 billion light-years away, the scientific community stirred with a quiet, electric excitement. The spectral data suggested the stars there were incredibly massive, perhaps up to 100 times the mass of the Sun, emitting ultraviolet radiation that matched theoretical predictions for Pop-3. If confirmed, it would be the first time humanity has ever seen the light of the universe's first stars, light that traveled billions of years just to reach us. Yet such observations have never been easy. The expansion of the universe stretches light to longer wavelengths, making the earliest starlight so redshifted and faint it is nearly lost. And those original stars, if they existed, lived too briefly to survive into the present day. Which means we are almost certain that all Pop-3 stars are long gone. But that doesn't make the search meaningless. In fact, with every new piece of indirect evidence, our confidence grows that Pop-3 truly existed. The chemical signatures of ancient Milky Way stars, the cosmic microwave background, models of galactic structure, data from Hubble and Webb, all of it blends into one layered symphony whispering the same thing. The universe once had a first generation of stars. There are no primordial hydrogen atoms left. Pop-3's ultraviolet light ionized them long ago. There is no perfectly pristine environment left for new primordial stars to form. But the ashes of that generation still linger in the most metal-poor stars ever discovered. Thus, the answer to the great question, are the first stars still out there, will always carry a dual nature, both realistic and poetic. Practically speaking, they are gone. They lived fast, burned fiercely, and exploded billions of years ago. But in a deeper sense, they remain. They remain in the light that has traveled 13 billion years to reach us. They remain in the heavy elements crystallized inside nebulae. They remain in the metal-poor stars we discover on the outskirts of the Milky Way. They remain in the very atoms that make up our bodies. And above all, they remain in the stories we tell, in the ceaseless journey of science, and in the endless curiosity of those who look up at the night sky. If someday telescopes or technologies of the future allow us to find a surviving Pop-3 star, still burning faintly in some remote corner of the universe, it would become one of the greatest moments in the history of astronomy. But even if that day never comes, the search continues, because we are not merely looking for a star. We are searching for the dawn of the universe, the first spark that set the stage for every star that followed, including the sun, the earth, and life itself. And so, in a soft and far-reaching way, the first stars are still here, within the starlight that travels through time, within ancient metallic remnants, and within every unfinished story the universe is still trying to tell. From the long search for those faint traces of the very first stars, we slowly realize that the most important answer is not about whether they still exist, but about how they left their imprint across the entire universe today. And when we step back to look at the full picture, we understand that every star, ancient or modern, is a single line in an endless story the universe has been whispering to us. The journey that brought us here has been filled with countless colors and rhythms of the sky. From the dawn of the cosmos, when the first stars sparked their light, to the diverse generations we've wandered through. The tireless red dwarfs burning for trillions of years, the quiet brown dwarfs that never quite ignite, the warm and steady other suns, the binary stars spinning like dancers in the night, the swollen red giants blazing in their final days, the heartbeat-like pulses of Cepheids, the fierce blue stars burning with scorching intensity, the Wolf-Rayet stars flinging stellar winds like cosmic fireworks, the gentle unfolding of planetary nebulae as small stars die and leave behind dense, diamond-like white dwarfs, the galaxy-bright supernova whose explosive ends give way to spinning neutron hearts and pulsars, and the silent, absolute shadows of black holes. Each type of star is a chapter in the cosmic epic, and together we have traveled through them all. Every shift of light and darkness, every cycle of birth, death, and rebirth. Stars do not exist in isolation. They are a continuous chain of cycles in which the ashes of one generation become the material for the next. All of it forms a grand life cycle spanning billions of years, shaping everything in the universe we know. And now, as the story closes, we return to the very first question of this journey. Are the first stars still out there? The gentlest answer is, they are present in everything that exists. We know Pop the third stars likely faded long ago, but their fingerprints run through every atom around us. The carbon in your cells, the calcium in your bones, the iron in your blood. They were all forged in the cores of stars that died long before our sun was born. This is not just poetic imagery. It is a fundamental physical truth of the universe. Every element heavier than hydrogen and helium was created in stars that burned brilliantly and then fell silent. And so, our sun, our planet, and we ourselves, the tiny beings listening to this story, are the descendants of ancient stars. Carl Sagan once said, "We are made of star stuff." And now, that sentence becomes more than a line of poetry. It becomes a reminder that we are deeply, inseparably connected to the universe. From cold physical processes, we rediscover something unexpectedly warm. The universe is not a distant stranger. It is our original family. Every breath you take was once gas drifting in some nebula. Every oxygen molecule in your blood once formed in the ashes of a supernova. And the light you see in the night sky is the whisper of countless stellar ancestors sending their stories homeward. As the tale draws to a close, we gently gather the threads of our journey. The first stars lit the universe. The generations after them formed, lived, died, and were reborn in new stars. Matter was reshaped over billions of years until eventually it formed a small blue world and life. All of it leading to one fleeting moment in cosmic history when a living creature looked up at the sky and wondered, where do we come from? And the soft answer is, we come from the light of the first stars. We come from the ashes of supernovae. We come from the tireless cycles of the universe. In the end, what we've learned is more than scientific fact. It is the universe's own fairy tale, a story whispered by every star in the night. So the next time you look up at the night sky, remember that every star is a quiet storyteller, and its light has traveled years, thousands of years, or even billions of years. just to reach your eyes. Let that light lull you to sleep, like a lullaby sung by the cosmos. Let its connection remind you that you are never alone. You belong to a family far larger than you ever imagined, the family of stars. And in the stillness of night, as everything around you falls into silence, the universe continues singing a gentle song, stretching from the dawn of time to this very moment, carried on the light of ancient stars. May you rest peacefully beneath a sky where millions of years of starlight whisper softly. You are the child of stars,